Hello students, we are about to enter the last set of material for this semester. So this is part 1 of the chapter 10 video, which is going to cover two theories, Vesper theory and valence bond theory. Today's video will just be about Vesper theory. The next video will be about valence bond theory. Both of those theories are theories that scientists use to analyze chemical bonding. And they both are built upon Lewis theory. So as I discussed in the first video from chapter 9, whenever you're thinking about a molecule, you always draw a Lewis structure first. From that, you can then apply what I'm about to teach you, which is called Vesper theory. And from that, you can then apply what is called valence bond theory. So let's get into today's video's topic, Vesper theory. All right, so we're going to start out with putting in your notes, what do those letters stand for? VSEPR. We just say Vesper theory for short. What it stands for is valence, shell, electron, pair, repulsion. All right, so first of all, shell, I've been using that here and there, is the old-fashioned term for principal energy levels. So essentially, this deals with the valence orbitals, the orbitals that contain valence electrons. So you can think of the valence shell as just the orbitals that contain valence electrons. So just so you know what shell means. Electron pair repulsion. So understanding this theory, really the most important word is repulsion. It's all about electron pairs repelling each other. So let's go ahead and put a key point on the board, and then we'll explain the theory. Once you understand the theory, it's not very hard. It's actually very, very common sense, this theory. And it deals a little bit with geometry, but not in a way that you're doing calculations with geometry. It's not like you have to remember geometry from high school. It's not that much geometry. So the key point of Vesper theory is this. The electron groups, and the electron groups are defined as either lone pairs or bonding pairs. So remember, when you do a Lewis structure, you can either have lone pairs, which is the double dots, or you can have bonding pairs, single bonds, double bonds, triple bonds. Those are all called bonding pairs. The electron groups that surround the central atom in a molecule are as far apart as possible because they repel each other. That's where the repulsion comes in, because they repel each other. So I think the best way to explain this is to just draw a little picture, and then we'll refer back to what I just have on the board. So let's just draw a generic molecule. I'm not even going to have real atoms with real names, just a central atom, CTRL. We'll just call that the central atom. And let's just, for our generic molecule, let's pretend that it's attached, or that 3 other atoms are bound to it. So I'll just draw them like this for my picture here. So you've got 3 other atoms bound to a central atom. And let's just remember, if you have a chemical bond, that means you're sharing electrons. So in this case, I'm just going to draw the double dots. Usually I have you drawing dashes to represent a bonding pair. But let me just come back to this to help you remember that these are indeed electrons. All right, so when you have a molecule, it's very important to remember that there's really several different electrostatic forces happening here. So let's remember, number 1, that there is a major attraction happening between these electrons, which, don't ever forget, they are negative. The electrons are negative. They are attracted to this atom's nucleus, which is positive because that's where protons live, as well as this atom's nucleus. I'm drawing little plus signs if you can't see me. So here you have a major attraction happening. there's attraction because positive things are attracted to negative things and vice versa. So these negative electrons in the middle are being attracted to him and him. And if you're being attracted to both by the right and by the left, you essentially will stay in the middle. Okay, so that's the whole point here. You're attracted to both nuclei. So if you wanted to write something in your notes, you could say bonding electrons are attracted to both nuclei of the two atoms that are bound. However, there's another major electrostatic force occurring in a molecule. Besides attraction, there's also a major amount of repulsion. And here's where it is here. These negative electrons, okay, let me go ahead and just write the negative up here so you can see it, are going to interact with these negative electrons, but not through attraction. This is a repulsion. There is a major repulsion between neighboring sets of electrons around the central atom. These electrons are negative, but so are these. And they literally don't want to be near each other. They are repelling each other. Picture my wrist being the central atom and the other atoms being my fingertips. They are repelling each other. Same with these two. They are repelling each other. Negative things don't want to be near negative things. Now, you may ask a good question, which is, well, how come he can be near him? That would be a good question. How come one electron can be near the other? Remember that within a bond, one is going to spin up and one is going to spin down. So if they can spin pair, they're plenty happy to be near each other. That lowers their potential energy and they're stable. But neighboring electron groups do not want to be near each other. Negative and negative will absolutely repel. And so the molecule is going to move these groups around until it can get maximum separation between the electron groups. And that's what I'm saying here. The electron groups that surround the central atom in a molecule are as far apart as possible. And that's because they repel each other. And one other key point, just to wrap this up to make sure that we're understanding it completely, is that the molecule will adopt whatever shape or geometry, okay, you can kind of interchange those two words, whatever shape or geometry allows for maximum separation between electron groups. And that's the whole concept behind Vesper theory. That's why Vesper theory is used to predict, let me add this here, used to predict the shape of molecules. Because it relies on this concept of getting maximum separation from the electron groups. And one other thing I'll go ahead and have you add on to your notes. The molecule will adopt whatever shape allows for maximum separation between electron groups, and that's because this shape will have the lowest energy. The lowest energy. At the end of the day, energy drives like everything. The lowest energy meaning the most stable. So whatever shape allows for these groups to get maximum separation is the shape that the molecule will settle into, because that's kind of the happiest place, the lowest energy place, the most stable situation for the molecule. And that's why we use this theory to predict the shape, figure out what the shape of molecules are. We are going to be kind of finally understanding why I keep drawing water like that boomerang shape. Okay, this is going to be all Vesper theory. So now that we have kind of the key concept, let's go ahead and teach how do you actually like apply Vesper theory? How do you do it? So with Lewis theory, the way that you do Lewis theory or apply Lewis theory is simply draw a Lewis structure. And we taught you in the last video how to draw a Lewis structure and showed you some of the fine-tuning aspects of it, resonance, formal charge, polarity, bond polarity, that kind of thing. So that all kind of comes from Lewis theory. To do Vesper theory or to apply Vesper theory to a molecule, you essentially need to draw what we call Vesper models. And that's how you apply Vesper theory to a molecule. So let me go ahead and give you the steps to draw a Vesper model. Step 1. start with drawing a Lewis structure. That's what I'm saying. You always start with Lewis theory before you get to apply these kind of more complex theories. So the first thing is to draw a Lewis structure. So let's go ahead and, as an example, let's go ahead and analyze the molecule HNO. Okay. I'm going to kind of just jump ahead to the Lewis structure, but let me give you the Lewis structure for HNO. If you had followed the steps that I've given you for drawing Lewis structures, you would get the same thing. So you could just kind of pause and see if you would get the same thing, but you'll notice, you know, how many pairs should we have? We should have, let's think, number of valence electrons, 1 plus 5 from nitrogen plus 6 from oxygen, that's 12. Valence electrons, that's 6 pairs. You'll see that we do have 6 pairs on my Lewis structure, and every atom is satisfied. Nitrogen and oxygen have octets, and hydrogen has a duet. So that's a Lewis structure for this molecule. Now, when I want to go ahead and start using Vesper theory or making a Vesper model from it, the next step is to do a little counting. We want to count the number of electron groups. Now, here's the thing. There's a new, you might not notice that I'm using this term, electron groups. I'm not saying electron pairs. I'm not saying, I'm very specifically saying electron groups. I was taught to call them effective pairs, but I'll use the terminology that your book uses. Count the number of electron groups around the central atom. So what we need to do is get this number. It's a really important number. In fact, when people mess up Vesper theory, this is the step that they usually mess up. So first of all, what is an electron group? What counts as an electron group? It's a new terminology. An electron group can be any one of the following. It can be a lone pair. It can be a single bond. It can be a double bond. Or it can be a triple bond. But all 4 of these options count as only one electron group. That's what I'm saying. We're not talking about electron pairs, because this is 2 electron pairs, this is 1. These are all equal in the sight of Vesper modeling. These all count as a single electron group. And let me explain. Well, first of all, let's get the number. So around our central atom, so your eyes are going to fixate just on the central atom. The reason is what's happening around oxygen doesn't affect the shape of the molecule in terms of these pairs repelling each other, because there's no atoms to connect to. It's kind of like the shape of my arm is all determined by what's going around the joint, around the elbow. So it's kind of like the same thing. You're going to fixate on the central atom and see what's going around him, and that is going to determine the shape of the molecule. So central atom is nitrogen, right in the middle. You count the number of electron groups. Here's 1, here's 2, here's 3. 3 electron groups is the answer. And that number is essential that you get that right. If you forget to count the lone pair, you're going to get the wrong answer, and everything from there on with your Vesper modeling will be incorrect. So 1, 2, 3, 3 electron groups. Now, why does a double bond count only as 1 electron group? The reason is because you're connected to, you know, the double bonds essentially married to each other. So this double bond cannot separate, you know, into 2 different, and they can't operate independently. Those 2 electron pairs operate as a team as far as repelling the other electron groups around it. So they basically are united together, the double bond. Same with a triple bond, it acts together. So that's why it only counts as 1 electron group as far as Vesper theory goes. Now, it does count as 2 electron pairs as far as giving it an octet, certainly. That's the reason oxygen has an octet, 2, 4, 6, 8. It does count as 2 electron pairs, but for Vesper theory, it counts only as 1 electron group. Okay, so you get that number. The number is 3. And then with that number, what you want to do is you want to arrange the electron groups according to the table. And what we're going to do is we are going to build this table together today in our notes according to the table. And then let's go ahead and add one more statement here. If all the electron groups are bonding pairs, okay? So if they're all bonding pairs, in other words, if they're not lone pairs, if they're one of these three bonding pairs, then what we can say is that the ideal electron geometries are achieved. And that part we will have to explain with a little bit more examples, but just write that in your notes for now. And then step 4 states this. Lone pairs require more room and will cause the bond angles to be smaller. All right, and so with that, we're also going to have to explain that with some examples. So let's leave that alone for now, but I just want you to have these 4 steps in your notes, and we'll return to explaining these 2 in just a second. So let's go ahead and start building what I'm calling the table. And then we'll do lots of examples. All right, so what I'm doing here is building a table with 1, 2, 3, 4, 5 columns. First column can be really small. The next 3 should be kind of equal sizes, and the last one can be pretty small. If I were you, I would do this on a fresh piece of notebook paper, and I would do it like landscape rather than portrait. Okay, so the first column is going to be called number of electron groups. The second column will be called angles. The third is going to be called ideal electron geometry. The fourth will say example. And the fifth is going to say hybridization. Now, hybridization is going to be a topic that we learn in the next video. And it has to do with what's called valence bond theory, the last theory. But what we want to do is include this on our table because it's really important for you to understand that the type of hybridization that's used, and even if you don't know what that means, we'll learn it soon. But even if you don't know what it means, it is fully connected to the number of electron groups. So all of these things are connected into one kind of complete story. Okay, so now let's start building this table here. So let me just make sure I'm saying everything that I want to say. Okay, so if you have, oh, actually, you know what? Before I do this, let me do one quick aside. Just one quick aside. If you have what's called a diatomic molecule, a diatomic molecule is just a 2-atom molecule. It can be homonuclear, which is something like H2. Homonuclear means the same nucleus, so basically 2 of the same type of atom. Or it can be heteronuclear, which is 2 different nuclei, something like HF. Either way, these are both diatomic molecules. If you have 2, you don't have a central atom. That's my whole point. There is no central atom. And you really don't use Vesper theory for a diatomic molecule. The shape of the molecule is just linear. It's just a straight line because the smallest distance between 2 atoms would just be a straight line. I mean, even if you move it, it's still a straight line. Okay, so a diatomic molecule, it doesn't really need Vesper theory. It's just a linear molecule, period. So when there's no central atom, there's nothing to say. Okay, so that being said, our chart starts with when you have 2 electron groups around your central atom. And by the way, if you're trying to figure out how far this is going to go, it's going to go 2, 3, 4, 5, and 6. Although you may want to save room because obviously you don't know how much I'm going to write yet. So, but it's going to go all the way down to 6. 2, 3, 4, 5, and 6. These are the only examples that we have with molecules in real life. Okay, when you have 2 electron groups, So in this thing, I'm going to have my central atom, I'll just have him be black. It's very generic, okay? We have a central atom, and you have 2 electron groups around the central atom. I'm not worrying about whether they're double bonds, triple bonds, single bonds, just 2 electron groups, okay? It's not about, we're not drawing Lewis structures right now. We're just thinking about how many electron groups are around that central atom. So here's my terminal atoms. The maximum separation that you can get, once again, picture my wrist being my central atom and my fingertips being my terminal atoms. The most that these can separate from each other is to basically be on either side of the central atom. So your angle is going to be 180 degrees. That's the maximum that these 2 lines, these 2 electron groups, can separate from each other. If they go farther down, they'll be closer than 180. If they go farther up, they'll be higher than 180. And frankly, if one of them comes out at you towards the board, he'll be closer than 180 too. So that's the bond angle, okay, between these 2 bonds when you have 2 electron groups around your central atom. What we call this electron geometry, we call this linear electron geometry because they're in a straight line. Linear electron geometry. And the classic example for a linear, I mean, there's lots of examples, but what I usually use is CO2. We have drawn the Lewis structure for carbon dioxide before, and we have found that he has 2 double bonds around his central atom. So if you had been asked to draw a Vesper model for carbon dioxide, you would start with the Lewis structure. You would draw this, okay? Then you would look at the central atom and you would count how many electron groups are around him. He has 1, 2. That's why he's the example for 2. Now, how do you turn the Lewis structure into a Vesper model? All you have to do is add that bond angle, because now you're describing the shape of the molecule. It's a straight line. And CO2 is a linear molecule. It's not like water where it's bent down. CO2 is a linear molecule. Now, the hybridization, without even telling you what any of it means, I just want you to write SP. SP, this carbon molecule undergoes what's called SP hybridization. Carbon atom undergoes SP hybridization. Just jot that in your notes, and we're going to leave that for next video. Moving on to 3. What happens when you have a central atom, but in your Lewis structure, it has 3 electron groups that are trying to kind of push each other around and get as far apart from each other as possible? What shape will it adopt? Well, what it will adopt is kind of like this Y shape. So 3 groups around your central atom. And once again, I'm not differentiating right now whether they're double bonds or triple bonds or single bonds or lone pairs. Although if I'm having them terminate in atom, I'm talking about bonding pairs. But anyhow, the shape or the geometry will be 120 degree angles. If you can think about a circle is 360 degrees, divide that into 3 quadrants, you're going to do 360 divided by 3 is 120. So it does make sense that it would be 120. Now, why is that as far as they can get from each other? It's because if you, say you wanted to move this pair a little bit, and by the way, we're not talking, don't think about the atoms. It's the electrons that are trying to separate from, remember from my starting, what I wrote on the board at the beginning. These are trying to separate from each other. And if he went a little bit closer, maybe to try to get away from him, he'd get too close to him. So that's why he's up there. So 120 degrees is as far away as they can get from each other. This type of electron geometry is what you would call trigonal planar. Trigonal planar. Now, it's a little hard to see on the board, but it's called trigonal planar because this type of geometry lies flat on a plane. It's not like one of these electron groups is being pulled out towards you or towards the camera. It lies flat on a plane. That's why it's called trigonal planar. And a good example would be something like formaldehyde, CH2O. Let me take a little bit of time with you. Hopefully you can have a little bit more room. But let's draw the Lewis structure for CH2O. Let's start with the Lewis structure, and I'm going to show you how to turn it into a Vesper model. carbon. You can pause the video, by the way, if you like, and see if you can do it yourself. So I have that it would have 6 pairs of electrons, of valence electrons on my Lewis structure. Carbon would be central because he's listed first. I'm just going to do H's on either side and oxygen on top. Connect the pairs together, or connect the atoms together. The next thing that I do with my Lewis structure. Then I start assigning lone pairs, but hydrogen's already satisfied, so I'm going to start satisfying oxygen because he's the other terminal atom. Now that I've used all 6 pairs, I need to check and make sure everybody's satisfied. Carbon is not. So I'm going to go ahead and reassign one of those lone pairs as a bonding pair. I'm a little bit squished. I'm scared you can't see that, so let me stretch him out a little bit. This would be my Lewis structure. And that's a great Lewis structure, okay? When I am done with my Lewis structure, I fixate on the central atom. I count the number of electron groups. 1, 2, 3. 3 electron groups means that he will be in this type of arrangement, this shape. So while this is the Lewis structure, and it is the Lewis structure, the Vesper model takes that information but draws it like that. So it would be something like this. And you know what I would do just to make it a little bit nicer? I'm going to flip my oxygen down to make it look like a Y. This is the Vesper model. And it becomes the Vesper model the minute I label the angle, 120. Without the angle labeled, it's not a Vesper model because you're asking people to just take your word for your art and know the angle. You've got to have the angle on the Vesper model. And so that is the shape of formaldehyde. It's not shaped like a Lewis structure. The Lewis structure was never intended to give you the shape. It was just intended to tell you what type of bonds hold it together and where the lone pairs are. The Vesper model indicates the shape of the molecule and is really useful for understanding things like polarity and boiling point, melting point. I mean, it ends up being really important to know the shape. So that is the Vesper model of formaldehyde. I'm going to erase this and get a little bit more space. Well, I just drew it, but I would have put it right here. I know I'm kind of making this a little bit hard on you to take beautiful notes, but you can always rewrite it. The type of hybridization, sp2, would be the type of hybridization, and we're going to leave that alone. Let's go now to 4. What happens when you have 4 electron groups around your central atom? So let's draw a central atom. How could they accommodate, you know, we've got a 3D world around that central atom. How can you spread out those electron groups so that they maximally separate? Well, the way that they would do is they would adopt this kind of bond angle here. So here's one of your terminal, or this is one of your electron groups right here, would go straight up. I usually draw 2 down, but this time the downs are a little bit closer together. And then I draw one that's a wedge. And the wedge in chemistry indicates that you're entering the back part, you're going kind of into the board. Frankly, this one here, some people will do like another wedge, just a different color, to indicate that it's actually coming out at you from the board. That's really, let me go ahead and do that. Just a different type of wedge. This one's coming towards you. This one's going into the board. Picture a tripod camera where this is the camera and this is like the 3 feet on the stand. The type of angles that this type of molecule would adopt, these are all going to be what are called 109.5 degree angles. Okay, it's not 360 divided by 4 because now we're entering a 3D world. Okay, so it's not just a 2D 360 circle. So just, it's always 109.5, sorry, 109.5, you can memorize it. But the key here is that all the angles are 109.5, not just the one that I labeled, all of them are. It doesn't look like that because I'm trying to draw on a 2-dimensional surface, but if you look at models, you'll see that they're actually all the exact same angle. Now, what is that? And that is as much as these electron groups can separate from each other in this 3D world that we live in. The name of this electron geometry, this is called tetrahedral. tetrahedral. And you can see the 4 tetra prefix being used. Here you can see the 3 prefix being used. So tetrahedral. The classic example of a tetrahedral molecule would be CH4, methane. CH4's Lewis structure looks like this. Once again, you always start with the Lewis structure. And when you get that Lewis structure, you look at the central atom and you count 4 electron groups around it. And that's why it adopts the tetrahedral geometry, okay? And the way that you would draw your Vesper model is like this. 1 up, 2 down, maybe one of them kind of facing forward, and one of them facing backward. And technically, because all the angles are the same, you can really label any angle 109.5 degrees, and I would know, and anyone looking at it would know, that it applies to all the bond angles. The type of hybridization, sp3. Now, without getting into it, you can see a little bit of a pattern. When it was 2, there were 2 letters. When it was 3, there are 3 letters, because you call it sp2, but you can think of it as sp and another p, spp, 3 letters. 4, sp3, so sppp, that's 4 letters. So there's a little pattern there, and we will kind of understand that later. Let's move on to finishing out our table. We have to do 5 and we have to do 6. So, okay. What happens when you have 5 electron groups around the central atom? So let's go ahead and give our central atom there. When you have 5 electron groups, this is the most complicated one to try to draw, but I want you to learn how to draw it. One of the groups will go up and one will go down. And these are what we call our axial axis, AXIAL. It's the vertical axis of the molecule. So these 2 will go kind of one up, one down. The other 3 actually are on what's called the horizontal plane. So if you took this molecule and thought about looking at this plane, like the horizontal one, like this one here, what it is it's a trigonal planar on that plane. So it's actually on this plane, they're 120 degrees from each other. So you would just draw one right here. Oops, I'm having these guys be white. One right here, and then you would have 2 right here. And it's essentially, this is that Y shape on the horizontal plane, that trigonal planar shape on this plane, combined with these 2 on the other plane. Now there's 2 sets of angles. One of them is the 120 degree angle that we know from trigonal planar, 120 degrees. And I usually just label this one, although technically it's also this angle and also that angle, but I usually label this one. And then the other angle is a 90 degree angle between this axis and the horizontal axis. So that's how I usually draw this type of geometry where you have 5 groups being accommodated. What it's called trigonal. The electron geometry is called trigonal bipyramidal. Now, bipyramidal means 2 pyramids. It's awfully hard to see, but if you looked at models, if you took like faces or like index cards and placed them on all the angles and made like a 3D geometric figure, what you would have is a top pyramid going towards the top atom and a bottom pyramid going towards the bottom. And that's why it's called a trigonal bipyramidal. It's like 2 3-point pyramids is the shape that this would end up being if you placed faces on it. That's why it's called trigonal bipyramidal. The example that I'm going to give you is PCl5. And I'm just going to go straight to the Vesper model here. The phosphorus being the central atom, and you've got 5 chlorines. So one will be in this position, one will be in this position, one will be in this position. One will go up and one will go down. Now, a Vesper model has to contain everything that the Lewis structure had. So I've got to actually, it's a little bit tedious, but had we drawn this Lewis structure, and you certainly could just to practice, you would see that all of these chlorines have 3 sets of lone pairs. That's why they have their octet. They've got to have their octet or else it wouldn't exist. And we're almost, so that's got to be included on your Vesper model, all of the information that was there in Lewis. And you've got to have the angles. You can't expect people to just love your drawing. You've got to have the angles. So we've got to have at least one of the 90-degree angles labeled. I always just do the top one because it gets kind of messy. And then I always do this interior 120-degree angle right there. And that would be how you would draw the Vesper model. The hybridization, SP3D. Once again, 5 electron groups, 5 letters. And the last number is 6. Now, why do we stop with 6? It's not just because we get tired. There are no molecules that ever have more than 6 electron groups around their central atom. They don't exist. There's no central atoms with 7. Okay, that's why we stop at 6. So, what happens when we have a central atom with trying to accommodate 6 electron groups around it? The way you would draw this on paper would be to have 1 up and 1 down. And this time, almost like a star shaped. And try to make them all equivalent to each other in terms of kind of angle, because they actually all are 90-degree angles. Like I said, it won't look like it on a 2D drawing because we're trying to represent a 3D thing in 2D. But if you look at your book and look for examples, where they have artists drawing it, you can see that they actually all are 90-degree angles. What we call this geometry of these electron groups, like this type of shape, we call this octahedral. It's a little bit misleading because you see 6 and you think it should say hexa, but it's called octa. And the reason is because if you put faces on it, like little index cards all over the molecule, it would make what's called an octahedron, an 8-sided figure. But don't worry about it. Just understand that it's called octahedral electron geometry. And the example would be that I'll give you is SF6. It's a real molecule, sulfur hexafluoride. If you did the Lewis structure, you would see that sulfur has 6 electron groups around it. And so you would end up drawing the Vesper model just like this, where the sulfur's in the middle. The fluorines would occupy this type of shape. There would be 3 lone pairs on all the fluorines, okay, if in your Lewis structure. And it becomes a Vesper model as soon as you draw it to the best of your ability in the shape that it's supposed to be and include the angle. And that makes it a Vesper model. Hybridization would be SP3D2. Okay, so now let's so we've got the whole chart, we've got it all set up. Let's go ahead and do a new molecule from start to finish and apply what's called Vesper modeling. Okay, let's go ahead and do this molecule, CH, let me think. I'm trying to think if I want to just do this one. Trying to think of what would be the most beneficial for us right now. Yeah, fine. This is fine. CHCl3. Okay, what I want us to do is, we have a molecule. Let's ask the question, can you determine the electron geometry of this molecule? Essentially, I want to know, of those 5, linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral, what is the electron geometry of this molecule? We have to start with a Lewis structure. So, following the rules that are given in the previous video, the first atom is the central atom. Hydrogen can never be central, by the way. So, and by the way, carbon is pretty much always your central atom because he always forms 4 bonds. But So carbon is your central atom, and he's listed first. You have 4 other atoms, and you would just arrange them around. And I put hydrogen there. You could have put hydrogen there, that would have been fine. But you just arrange them around the central atom. And remember, Lewis theory is always very grid-like, north, south, east, west positions, unless you have like 5 or 6 and you just have to, make it kind of bigger, like the PCl5. But if you only have 4, take north, south, east, west. Now, number of valence electrons, 4, plus 1 for hydrogen, plus 3 times 7 for the chlorines. That's 21 plus 5 is 26. Divide by 2 to get pairs, 13 pairs. Connect them together. Assign lone pairs to the terminal atoms. Trying to satisfy them. So I've used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. He's already satisfied. 11, 12, 13. Okay, so now I have a Lewis structure because I've used all my pairs. Every atom is satisfied. And I don't have any resonance structures because I'm not forming double bonds. So that's my Lewis structure. What shape is it? I go to my central atom. I count the number of electron groups. Okay, here's 1, here's 2, here's 3, here's 4. I make sure that number is correct because that number is going to determine everything. It has 4 electron groups. And so now to do the Vesper model, I just have to take that molecule and draw it correctly. And 4 means I'm drawing them in that 109.5 tetrahedral geometry. So one of the positions will go up. And just for the sake of kind of a nice picture, I'll make this one be H, but technically it really could have been any of them. I'll make these 2, or sorry, these 3 go to chlorines. And I got to make sure I keep the previous information. You can't lose information just because you're doing a Vesper model. These still have electron groups, or sorry, lone pairs. And it's almost complete. What do I need to make sure your Vesper model is complete? You need angles. At least one of the angles has to be labeled. I'll just, for the sake of it, label this one, 109.5 degrees. Okay, so that's the Vesper model of this molecule, and that is the shape of it. I mean, if you could see that molecule with your own eyes, that's what it looks like. It doesn't look like this, like a T, okay? It's shaped like this. It's a real shape, and that's the shape of this molecule. Let's just do one more. All right, how about we do, trying to think of one that we haven't done together. How about let's look at the shape of, how about of chlorate, ClO3 minus. Let's do this. Let's find out what he looks like. Chlorate. All right, we need a Lewis structure. See if you can draw your own Lewis structure, and I'll draw mine and see if they match. Alrighty. So this is the Lewis structure that I got, and let's make sure it's correct, okay? Correct just means that you can say yes to both questions. Did I use all my pairs? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yes. Does every atom have an octet? And the answer is yes. So this Lewis structure is correct. And so you could analyze the Vesper theory on it. I do want to point out, just as I was doing it, this this molecule will have multiple resonance structures. In other words, alternate forms. I can tell that this is not the best form for ClO3 minus. Now, if you gave it to me on a test, I would mark it as correct, unless I was asking you for the best form. If I just asked you for, give me a Lewis structure, it's correct. It is a Lewis structure. However, I know it's not the best form because when I look at the formal charges on the atoms, let's just look at chlorine, for instance. Chlorine is supposed to have 7 electrons, 7 valence electrons from the periodic table. In the circle, it only has 5, which means it has a formal charge of 2, plus 2. And the oxygens, if you did them, they all have formal charges of -1. Notice all the formal charges do add up to the charge. So I know that's another way of checking that it's correct. I can draw a Lewis structure with fewer formal charges. Let me go ahead and just do it. I know we're trying to do Vesper theory, but let's use this as an opportunity to review resonance and formal charge. If I relocate that lone pair, I'll actually reduce the formal charge on the 0. On the oxygen. And if I do it there as well, he'll have his, for this one. And if I do it there as well, he'll also have it. So chlorine, if I have this Lewis structure, do I still use 13 pairs? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And what are the formal charges? The formal charges on this oxygen would now be 0, 0 on him, 0 on him. And what would the formal charge be on the chlorine? Well, he's supposed to have 7. And now he has 1, 2, 3, 4, 5, 6, 7, 8. He now has a -1 formal charge. So this one has fewer formal charges. The absolute best Lewis structure, if I had to guess, would, see with resonance you can kind of play around with it a little bit here. I am guessing that the best Lewis structure would be this one, because remember, if you can't avoid formal charge, in other words, if you can't get zeros on everybody, the best formal charge would be the one that has the negative formal charge on the most electronegative atom. With this Lewis structure, still 13 pairs, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. But this time when I look at the formal charges, he is 0, he's 0. Chlorine now has a formal charge of, let's see, 7 minus 1, 2, 3, 4, 5, 6, 7. Chlorine has a 0 formal charge now. And oxygen is the one that has a -1 formal charge. And that's better because oxygen's more electronegative. So my best Lewis structure is going to be this one here. So that's the one that I'm going to go ahead and analyze for Vesper modeling. However, I want you to notice something really kind of useful and maybe reassuring. That either way, the number that determines everything around the central atom, 1, 2, 3, 4, 1, 2, 3, 4, is still 4. So whether you had analyzed this one or you had analyzed this one, you would have gotten the same electron geometry for your Vesper model. But let me go ahead and just draw the Vesper model for the best Lewis structure. And once again, I know I'm kind of being a little bit advanced here. I don't necessarily need you to get to that point where you can figure out the best one all by yourself. On the exam, I'm not going to ask you to do that. I will either just ask you to give me one acceptable Lewis structure, any of them, That one would have been fine. Or I will present you myself with alternate forms, and you'll have to determine which is best based on formal charge. But I'm not going to have you do what I just did, which is figure it out yourself, because it's a little bit advanced. But for some of you guys, I think can handle that, and maybe you found that helpful and to understand it fully. That's your best Lewis structure. Let's go ahead and analyze it. We've got 4 electron groups around our central atom. That means it is going to be the tetrahedral electron geometry, okay? And so now we're going to draw this here. Now, one of those groups is a lone pair. Usually when there's a lone pair, I draw it going in the up position. And I draw it in a bubble because it's not like there's an atom up there. I just draw it in a bubble. And then the other groups, I'm just going to arrange around. I'll just do the double bond to the O here. I'll do the other double bond to the O here. And I'll just do the single bond backwards. And that would be the Vesper model. Now the angles, 109.5 degrees. In just a minute, I'm going to explain why, in fact, what you would want to do is draw a less than 109.5 degrees there. So let's return to that in a minute. Maybe draw it in there for a second. I want to transition now into the effect of lone pairs. So that's just a little extra Vesper modeling practice. And that would be the shape of your chlorate molecule. All right. So now let's go ahead, and this is really kind of where our video is going to finish up for today. We're going to stop with the effect of lone pairs. That's going to be kind of our last topic. The effect of lone pairs on, let me say, on bond angles and on what we call molecular geometry. That's what I want to finish with here. Okay, in order to teach this, let's start with something really simple. Let's start with 3 very simple molecules. Let's contrast CH4, methane, with NH3, ammonia, and with H2O, water. Very simple molecules. All right, what I want to do is draw the Lewis structures for all 3, okay? So if you want to do it yourself, just to practice, go ahead and do it. But let me just draw Lewis structures for all 3. These are so famous that I've got them memorized. All right. What you will notice about all 3 molecules is that they have something in common. All 3 have 4 electron groups around the central atom. He does, now they all come in the form of bonds. He has 1, 2, 3, 4. Remember, lone pairs count. They absolutely count as electron groups according to that first definition that I gave. It has 4 electron groups that need to push each other around to try to find space around that central atom. And so does the oxygen. He also has 4 electron groups around his central atom. 1, 2, 3, 4. They don't have to be bonds to count as electron groups. They can be lone pairs. Because they're all 4, they all will obey that 4th line on that chart. They'll have 109.5 degree angles, tetrahedral electron geometry, and sp3 hybridization, all of it. So let's go ahead and draw Vesper models for all of them. Now, that's that tripod camera thing. So CH4 I actually had already done for you. That was my example. And the bond angle, 109.5. Okay, so you remember the bond angles are all equivalent. They're all 109.5 for methane. And you would call this electron geometry. By name, you would say it has a tetrahedral electron geometry. That's what you would say. Now, when we use the term electron geometry, we are talking about the geometry of not the molecule, but the electron groups. You're actually fixated on the electron groups and how are they arranged geometrically. In contrast, there's another concept called molecular geometry, which is equally important. Molecular geometry is asking a different question. What is the geometry of the molecule, really of the atoms? So when you think molecular geometry, you want to think about almost like encircling the atoms. Like, what is the geometry of the molecule itself? And what you would see is that as long as these are all leading up to atoms, like as long as they're bonds that have atoms at the end, the molecular geometry and the the molecular geometry and the electron geometry is the exact same name. It's still a tetrahedral geometry, the atoms, but also the electron groups. Let's move over to NH3 and you'll see kind of what I'm getting at here. Let's draw the Vesper model of NH3. With this one of those is a lone pair. And remember with chlorate earlier, I said, go ahead and put it in the up position in a bubble. And it kind of makes for a nice drawing. So this is ammonia. Now, two things we need to notice. First thing is this, the lone pairs. The lone pairs are not stretched up to another guy's nucleus. There's no atom up there that they're attracted to. Because of that, it's like a rubber band that's not being stretched. It's kind of fat, or it takes up a lot of space. It's not like pulled up nicely. It's like, ooh, it's like flat. It's like kind of fat. So what it does is it actually pushes those other groups a little closer together. It like elbows them around and it pushes them closer together. So when you have a lone pair, your angle is smaller than it normally would be. So instead of just being 109.5, what you have to do is write less than 109.5. It's a little smaller. It's more like 107, but it's a common thing to know that the bond angles are smaller when one of the positions is a lone pair. So you're going to have to include that less than in order to kind of show that effect on the bond angle. The electron geometry is still tetrahedral because I want you to see the electron groups are still a tetrahedron, that tripod camera thing. However, your molecular geometry, talking about the geometry of the molecule, understand that the molecule is kind of defined by where the mass is, the atoms. That molecule is not a tetrahedron. There's no atom up there. It doesn't look like that tripod camera. There's nothing up there. There's some electrons pushing people around, but there's no atom up there. So the molecular geometry is not just the same. It's not tetrahedral. It's actually going to get a new name. And what it is called Trigonal Pyramidal. Now you got to be careful. We've already encountered trigonal planar and trigonal bipyramidal. So this is different, trigonal pyramidal. But you can see it makes sense. It's like a three-point pyramid. The ammonia molecule is shaped this way, and it is going to affect its polarity and some of its chemical properties. So it's important. It's a very important part of the ammonia molecule that it is shaped that way. So that is, in fact, you know what? Let me just mention the polarity for a minute. Why not? Once you can see the shape of a molecule, you can understand whether the molecule is considered polar or not. And I talk about this in the intermolecular forces video. When you look at like one of these nitrogen to hydrogen bonds, and you use the electronegativity scores to figure out if it's polar or not, nitrogen is 3.0. Hydrogen, let's just remember that. Nitrogen is 3.0, I believe. Hydrogen, I believe, is 2.1. So the difference in the electronegativity scores is 0.9, which means that it is a polar covalent bond, with the nitrogen being the more electronegative atom. Okay, let's talk about this real quick. Which means these electrons are all shifted up towards nitrogen. So you will have what's called a partial negative up near the nitrogens, because all of those bonds, all three NH bonds are polar. And so all these electrons are actually, they're not in the middle, they're shifted towards nitrogen, and wherever they shift, you're going to write partial negative. And they're shifted away from the hydrogens. So you could just have like the north of the molecule be considered negative and the south of the molecule be considered positive. That means that this molecule is what we would call a polar molecule. A polar molecule has a positive side, a partial positive side, and a partial negative side. In this case, the way that I've drawn it, the north is negative, the south is positive. That's what it means to be a polar molecule. And we really need to know, we needed to know two things. We needed to know that the bond was polar, but you also needed to know that the shape of the molecule meant that like the north would be different than the south. Because if the molecule was symmetrical, they would cancel each other out. I'm not going to go too far into that because we're gonna leave that alone. I'm just going to talk about it in terms of this molecule. But anyhow, it is a polar molecule because of its shape. Let's return back to our main focus, which is the effect of the lone pairs. Water, H2O. Let's draw the Vesper model. So I'm going to have oxygen here in the middle. This time I've got two lone pairs. So I still make one of them the top. And when I've got two lone pairs, I usually make the other lone pair go to the side, just for the sake of kind of a nice picture. And then the other two positions are the ones that lead to the bonds to hydrogen. And that is the Vesper model of H2O. Okay, you do have 4 electron groups. They are occupying an electron geometry that is tetrahedral. By the way, this colon is the answer to this question. Hopefully that's clear. These are the electron geometries. Okay, let's talk about the angle. Now this time, instead of just having one lone pair, you actually have 2 that are basically being kind of pushy and taking up more room than normal. And because of that, this angle is less than 109.5 degrees. I actually have 2 less than signs there. It's around 104.5 for water. It's even more smaller than usual. That's it, like a twofold negative deviation because of the 2 lone pairs. So that's the first thing. With 2 lone pairs, you'll have even smaller bond angles than with 1 lone pair. And the second is, what is the molecular geometry of this molecule? Well, let's look at it. If you kind of enclose the molecule and just look at the atoms, what shape do they adopt? You can see they adopt this kind of boomerang shape, and that is called bent, B-E-N-T, bent. So the molecular geometry name of it is not going to be the same as the electron geometry if you have lone pairs. It's only when they're all bonding pairs that the 2 names will match. Now let me go ahead and almost be finished. Let me say, in your book, if you have your book, go ahead and turn to, we want to look for what's called table 10.1. And let me see if I can find the table. It's on page 436. What I've done on the board is kind of a simplified version of what this table is. In this table, you'll see it's pretty much the same thing. You have the electron groups, and it goes from 2, 3, 4, 5, and 6. I just kind of actually fixated here on the 4 section, and I taught you just now, just so you can see what this is, that when all 4 groups are bonding groups, yes, the electron geometry is tetrahedral, but so is the molecular geometry. The angles are 109.5, and there's your example. This is exactly what I just taught you. But when you have, one of those groups, when one of them is a lone pair, your molecular geometry is now called trigonal pyramidal, and you have a deviated angle less than 109.5. So the issue here is that these types of new molecular geometries, there are new names for all of these. There's seesaw, T-shaped, square pyramidal, square planar. You do not need to memorize these new names. I do want you to kind of understand the table, and say if you were given a molecule that required you to use the table, that you could find out what your molecule kind of matched. So say if you had, okay, I've got 5 electron groups, but 2 of them are lone pairs. That means your molecular geometry would be T-shaped. Now you got to kind of think about it, and you got to kind of play with it a little bit, but use the examples to understand it. It's essential that you actually kind of think through this, okay? This kind of stuff takes a little bit of work. Use this. These are so helpful to look at the examples. So I do want you to understand table 10.1, but it's not like you're memorizing it. You will have access to it on the test. So in the Blackboard announcement where I make this, where I post this video, I'm going to assign you your last lab assignment, which is going to be an 8-point assignment. What I'm going to give you is a website that you just click on, and I'm going to ask you, based on your last name, to use the website to basically, it's a simulation website where you can basically create molecules. It's very simple to use. Like, I usually don't like things like this, but I think it's very simple, and it's really nice to see the geometries. I'm going to give you 4 molecules that I want you to basically create using the website, and I want you to send me photos of those 4 molecules. Send me from the website. It'll take you a few minutes to kind of play with the website and figure out how to work it, but I essentially want you to create 4 molecules. I will assign which 4 I want you to make from based on your last name, which will be in the Blackboard announcement. And I think I will give you 3 of the molecules from my lecture and 1 that I did not talk about. So you can kind of push yourself to draw a Lewis structure and figure it out, the Vesper model out by yourself. So it will allow you to kind of see this the molecules in 3D, and it really, really is helpful. So it shouldn't take longer than half an hour at most from start to finish to figure out the website and snap a few photos of 4 molecules that you make. It could take as short as 10 minutes if you're pretty quick with the website. That's your last lab assignment. I'll put a due date on the announcement. So this is Vesper modeling. I didn't talk much about polarity of molecules. I'll probably not say too much more about that, more than what I just said about ammonia being polar. By the way, water, is it polar or is it not? The OH bond, definitely polar because of the difference between O and H. You could calculate the delta EN if you wanted to prove that to yourself. The oxygen is the more electronegative atom. So you're going to have a partial negative in the north. You're going to have partial positives. You can either write them on both hydrogens or just put a partial positive towards the south. So yes, water is a polar molecule. And by the way, that's a hugely important concept for all of science, that water is a polar molecule. But now you know why. It has to do with the bond polarity as well as the shape of the molecule. Anyhow, that is the end of this topic. Looks like my camera just froze, so that was good timing. And thank you very much for listening. Good luck with the lab activity. Hopefully you will find it useful.